So with chi-square distribution, it's not a normal distribution. It says like the t-distribution, the shape of the distribution is a function of its degrees of freedom. The higher the degrees of freedom, the closer that the graph will approach normality, meaning it will look like a normal distribution if the sample size is large enough. Just like with t-distribution, it'll approach being normal if the sample size is large enough. And we did distributions or confidence intervals with means. We did confidence intervals with proportions. Now we're going to do confidence intervals with variance or standard deviation. All right, so the formulas are in the PowerPoint. Again, this is chi, so that will be chi-square. The main difference, I guess, is that we're not going to have like a positive and a negative. You know, with the t-distribution, we didn't have a positive and a negative critical value, but with z we did because of symmetry. You know, on both sides, it was the same value, but one was positive and one was negative. But we always used the positive one because when we plugged them into our formulas, it didn't matter if you plugged the positive or negative in. The negative sign was going to go away if you plugged the negative in, right? Because one of our formulas we used had, for sample size, the thing was squared. And when you square anything, the negative goes away. The other formula we used had a plus or minus in it. So if you plug in a positive or a negative critical value, then it didn't matter because the signs were going to work themselves out. With the t-distribution, the formulas we used, also it didn't matter, but we only got that one value out of the table, remember? We only got that one critical t value. We didn't ever get two. Well, with chi-square distributions, we are going to get two. And they're not going to be the same number. There's going to be one, and since it's not symmetrical, you see it's skewed to the right. That's where the tail is, so it's skewed to the right. But we're going to have, one like over here, and then one maybe over here. Okay? And since the values here start at 0, they are, they're not going to be negative. Neither one of them are going to be negative. And they're going to be different. They're going to be vastly different. One of them may be 2 point something. The other one may be 19 point something. Okay? So we're still going to use a chart. We have that table, I think it's G, that we can use to find these values. We've got to figure out how to find the values. So that's the main thing. Once we figure out how to find the values, then we're just plugging this stuff into a formula. Now, it's not the plus or minus formulas like we were using before, but the formulas are still similar. So you can see this has the square on it, so this is for what? This is for variance, right? So we're going to figure out this number right here. This is a critical chi-square value, and this number right here is a critical chi-square value. I know it's a variable, but there'll be numbers, but they'll be totally different. Okay, that's where I guess this is the biggest part that's different, is that instead of having a plus or minus formula, remember I showed you how to kind of write your answers in a form like this with an interval? So this is just writing it in this interval form. And the big difference, again, is the way you find the critical values, and they're both going to be positive numbers. It's just one of them's going to be on the left and the other's going to be on the right. I've even seen some textbooks, instead of putting alpha over 2 here and 1 minus alpha over 2 here, actually call one of them the left and one of them the right critical value. one of the last textbooks that I used, I copied over some of my PowerPoints because I wanted you just to see that it can be written just a little differently. I believe it's right here. And I'll show you. And of course, this is for the variance. Standard deviation, you just take the square root of all that. All right, so this is a different book that I've used before. And see if they have the formula here. I haven't seen the formula yet. Yeah, so they refer to the one on the left as the right critical value because it comes from the right side of the graph. You don't really have to know that, but it comes from the right side of the graph. And they refer to this one as the left critical value because it comes from the left side of the graph. Okay? And then, of course, if this is the population variance, confidence interval for variance, if you want standard deviation, we just take the square root of everything. Okay? So let's look at how to find one of these critical chi values. All right. So let's look at the book. Let's look at the problem that comes from the book that's with your PowerPoint. This is one of the first PowerPoints. All right. And you've probably already read through this. But it says the quality control supervisor for bottling plants concerned about the variance of fill per bottle. Regulatory agencies specify that the standard deviation of the amount of fill should be less than 0.1 ounce. To determine whether the process is meeting this specification, the supervisor randomly selects 10 bottles. So 10 bottles. So that would be what, like N equals 10, right? This person selects 10 bottles. Weighs the contents of each and finds the sample standard deviation is 0.04. Compute a 95% confidence interval for the standard deviation of ounces of fill for the bottle. All right, so the confidence interval level is important. You know, that's just like with the Z distributions and the T distributions. The alpha that you get from the confidence level is important. Now, for the Z distributions, we had that little table at the bottom of our table B to help us out. T distributions, we really didn't have that table, so we had to figure out the alpha, divide it by 2, and that told us which column to use on our T critical value chart. Well, with chi-square distributions, we need to figure out that alpha, and that's going to help us figure out where to look in our chart for the right and left critical chi values. So how do I find the alpha? This goes back to the very beginning of when we were doing the Z's and the confidence intervals we do, and I think I heard someone say that. 1 minus, in this case, what? 0.95. Where'd that come from? 95% confidence interval, right? Okay. So that means that that's equal to alpha. That's what alpha is. So what's 1 minus 0.95? 0.05, right? So that's my alpha, 0.05. All right, the way that our formula is, if we went back and we looked at the slide before, we have 1 chi-square, and the chi-square, that's not chi squared. It's just chi-square. It's a chi-square distribution. Okay, so this chi-square, this first one is sub alpha over 2, kind of like the Z and the T were. So it's sub 0.05 divided by 2. So we're going to have a chi-square that's sub 0.05 divided by 2. Or this chi-square is going to be, it's going to be sub what? 0.0, not everybody at once, 25. All right, you divide that in the calculator, or you do it in your head. It's better to do it in your head. That way you get good at mental math. All right. Now that's going to be, we're going to use that to find one of our critical values, right? And then the other one, if you remember the formula that we had up here, let's see. It says sub, can everybody see that? Sub 1 minus alpha over 2. So we've already figured out what alpha over 2 is. So now we just have to do 1 minus what we found alpha over 2 to be. So here's that right there. That's our alpha over 2. That's what we just figured out. So the other chi-square value, if you say 1 minus 0.025, you get 0.975. Right? Yes. Okay, thank you. All right. So now what we're going to do is we're going to figure out those critical values from table G. Now there's one more thing we need to use table G. And what is that? The degrees of freedom. And that is lowercase d, lowercase f, degrees of freedom. Is how that, and that's always n minus 1. So what does that equal to? 10 minus 1, or 9. All right. So we have columns here on our critical value chart. And let me see if I can pull that up real quick, just for the video purposes. All right, so look at the columns there and see if you can find the critical values and guess what they are without me even helping you do it this first time. And I'm pulling this up in your ebook. It's near the back of the ebook. Looks like it's page, let's see, this is F, there's F, there's G. All right, it's page 864. All right, so here we go. I'm going to zoom in a little bit because I'm old, so I got to be able to see these little numbers. All right, so we have this 0.0 or chi-square sub 0.025, and we have chi-square sub 0.975, and our degrees of freedom is 9. So here's our degrees of freedom right here. I'm going to clip this out so I can write on it. All right. So there's the degrees of freedom. So we're just using this row right here. So let's look for the one that's under 0.975. We got what? 2.700. And then let's look at the one that's under the 0.025. And notice they're both positive numbers. Okay, they're not like the z-scores. They're not one of them's negative and one of them's positive. They're not the same number. That's because of the way that the chi-square distribution works. All right. You know, think about what we're relating this back to. We're relating this back to variance and standard deviation. Can variance or standard deviation be negative? No, it can't. The way it's defined, standard deviation cannot be negative. Okay. All right, so we have our two critical values. So we're going to write down beside that 0.975, I'm going to write 2.0 or 2.700, and then between or beside the 0.025, I'm going to write down 19.023. All right. All right. So we got the first part that we need. So how about I show you graphically what are we actually finding? Now, the way that the graph of the chi-square looks depends on the degrees of freedom. And I believe that we had maybe example that had degrees of freedom of around 10, maybe. Yeah. So we had this right here that had degrees of freedom of 10. It's the light blue curve there. So what we're actually finding is we're finding a number over on this side. You know, one of ours was like 2.700. All right. And that one was on the left side. And then we had one way over here on the right side somewhere under the blue curve. It was 19.023. Was that it? 23. So that's what we're actually finding. You know, there's a area right here. Guess what that area is? 0.025. And then there's an area to the left of this. Now, do you have to know all this? No, but I would like for it to have a little more meaning to you. There's an area right there that was 0.975. All of that was. Okay. Now, this is the one that was on the left side, and this is the one that was on the right side. Remember the formulas? I showed you that formula that had the sub L and the sub R. Remember that one? So there's a couple of ways to remember which way or which critical value goes with which part of the formula. You know, the sub R goes on the left side, the sub L goes on the right side. So it's like just the opposite of what you would think. But here's the deal also. If you get confused about which one goes where, the bigger number that you get has to be right here. Because look, it's bigger than the middle. And the smaller number that you get when you plug it in the formula has to be on the left side because it's less than. So if you work them both out separately and you look at your two numbers that you get out, just remember the bigger one is going to go on the right. That's going to be the right endpoint. And the smaller one is going to go on the left. It's going to be the left endpoint. Because everything in the numerator is the same. None of that changes. Okay? Does that make sense? At least two people shook their head yes, so I feel confident that makes sense. I'm about 25% confident. All right, anyway. So now let's plug them in our formula and see if we can work our problem out. All right, so we had, in this problem, we can find the let's see, we want to find confidence interval for the standard deviation. So for this problem, we're going to have the square root of n minus 1 times s squared over that critical chi-square distribution, or critical chi-square number, sorry, that was 0.025. All right, and that's going to be less than the standard deviation, that's less than the square root of n minus 1 times s squared times the critical chi-square number, 0.975. All right, that's what we're going to do. We're just going to plug our numbers in. All right, so we have the square root of 10 minus 1, pretty sure we know what that is, times s squared. What was our s? Our s was 0.04 times 0.04 squared divided by that critical value that we got. So that was 19.023. All right, it's going to be less than the actual standard deviation. It's going to be less than square root 10 minus 1 times 0.04 squared divided by that 2.700. All right, so I'm going to get a calculator. So just, by this point, you know how to use the calculator that you have, hopefully. You don't have to use the Windows calculator like I do a lot of the times. One common mistake here is to not take the square root after you do all of your cool math stuff there. Make sure that you take the square root. All right, and I think if you look at the PowerPoint, it's going to do the variance first. If we were looking for the standard deviation, I don't see any reason to do the variance first. Unless the problem asks us for the variance confidence interval, the problem asks us for the standard deviation, the confidence interval for standard deviation. So I'm not even going to write down the variance. So I got 0.0275 if I round to 4 places for that one. And then see what I get for the other one. I got 0.0730 if I go to 4 places. And there's my interval. So my standard deviation is, I'm 95% confident that the actual population standard deviation would be inside that interval. One thing that the problem pointed out, it said that the company or whoever, I guess probably quality control, wanted the difference to be less than 0.1 ounces. So is that less than 0.1 ounces? Yes, it is. All right, so the new thing here, the only thing that's really different, is that we have to find that left and right critical value from table G. So let me see if I can find us another problem. I'm going to go into the homework and copy one up here, which I'm sure everybody's been working on. So I constantly update your grades in the grade book. Some people in here have close to 100 average. I think one or two of you have like 100, and then some 99 point somethings in here. So we're doing really good. All right, I found this one. Now, I will say this problem, whenever I pulled it up, it said the difficulty, like it usually tells me it ranks the problems. The difficulty's high on this problem because this isn't as, I guess I would say, as easy as, the ones that we've been doing. This is, when you start talking about trying to draw conclusions about standard deviation and variance, it becomes a little more complex. So I could understand if some of you were a little confused here. I think after you work a couple problems, it won't be too bad. All right. So what all do we need? You can read through the problem talking about green beans. Man, I love green beans. Got a sample of 56, a standard deviation of 0.15, and an 80% confidence interval. Okay. So write down what those are. What variables are they? Write down what that is. What would that be in our formula? Remember, this standard deviation is a sample. It comes from a sample, so it's S. And then 80% confidence interval. What does that even tell us? What is that used for? That's used for our alpha, isn't it? Okay. So we're going to have a critical chi-square. In the wrong place. Chi-square. That's going to be sub alpha over 2. So that's going to be, because that's our alpha there, so it's going to be sub 0.2 divided by 2. So we want to do this one first. So what's 0.2 divided by 2? If I had 20 cents and I had to divide it evenly, what would I have? 10 cents, right? So 0.2 divided by 2 is 0.1. And then our other critical chi value is going to be 1 minus that one. So it's going to be, and I put the square in the wrong place again, it's going to be 1 minus 0.1. What's 1 minus 0.1? 0.9, right? What's $1 minus 10 cents? 90 cents. 0.9. So you can do that mental math. All right, one last thing we need is the degrees of freedom. Okay? So degrees of freedom is going to be 56 minus 1 or 55. You may be wondering why I was laughing. Look at our table. That's probably why this was considered to be a tough problem, because our table doesn't have 55. Our table has 50 and 60. So, I mean, that's a problem. That was a good question. Let me see. See if we can use some symmetry, even though there's not any symmetry. Let's see if maybe if our table would work that way. Generally, if I'm working this problem and I have to figure that value out and I have to be 100% correct, I'm going to use technology to find it. Okay? There's ways to do it with calculus. We're not a calculus-based statistics class. There are calculators online where you just go in and type in the, your alpha and your 1 minus alpha, and it'll give you the answers for the critical values. Let me see if there's any symmetry I can use here This would be for an 80%, so we had sub 0.1 and sub 0.9. Those are side by side. The problem with that is, like, if I look up the value for 10 and then I look up the value for 5, 10 is not twice what 5 would be equal to. Okay? So I'm pretty sure, and I'm pretty sure I took some of these harder ones out where that you don't have the exact value for. But I'm going to find it anyway so that we can work out the problem. Anybody that's accessed that homework, have they noticed any of those? If so, I'll just give you credit on that. But I'm pretty sure I took the super hard ones out like this. All right, so I am just going to type in a calculator. Our significance level, let's see. Man, this page, I found this page right here, socialstatistics.com. Man, it just has the calculators here. So, like, it has the formula built in to where you wouldn't even have to use the t-square chart or the z-square chart. That's pretty nice. And then here's chi-square. Let's just make sure it works. How about that? So our significance level for this problem, let's do one that we can find in our chart. Let's do one for, say, degrees of freedom is 20. So our significance level, if we make it the same as that, then we could use the same column. We had, what was ours? 90 what? 90, no, it was 80%, wasn't it? It was 80%, so 80% was the 0.1. Let's see if I do degrees of freedom, 20. So I just want to see what this gives us. It appears that it's only given us 1. So if we go to 20 and 0.1 on your chart, did I type in 0.01? Yeah, I typed in 0.01. Everybody look though. So go to a different column. Go to the second to last column and go down to 20, and that's what's there. Okay, so this will work. Like if I went to 0.1, go back to the 0.1, go back to the one that's chi-square sub 0.100, and you can see 28.412. So this will work. Now, if you had to work out a problem where the degrees of freedom aren't there, it's best to use a website. What this website has is probably in the background, the person that wrote this, they have a formula they come up with, some, calculus formula that they have typed in the background, and whenever we put the numbers in, it just gives us the answers we need. So what we would need is degrees of freedom was 55. So this is going to be one of our answers. This is going to be the one that's sub 0.1. We might have an issue, but we'll see. Sub 0.1. So that's our critical value, 68.796. So for this one, the issue that we might have is that we may not be able to put in a significance level of 0.9 on this website. But we'll see. If not, we can find another one. Yeah, see, I don't see the 0.9 here so that I can put that in. So let me do a little more research. What I get for picking a random problem. Got to be careful where you click on the internet, though. So this one does the same thing. It just gives you one of them. This one I can enter it in. Okay. All right, check this one out. This must be a website dedicated to me, by the way. MassCelebrity.com. I'm just kidding. All right, so let's make sure it works though. Let's put in what we got first. So I'm thinking that we can put in our alpha and then 1 minus our alpha. So first we used an alpha of what? We used an alpha of 0.2, wasn't it? Isn't that what alpha was equal to before we divided? And then the degrees of freedom was what? 55. So let's see if that gives us what we need. Look at it. It's telling you what you're doing there. What's it doing there? Where's the answer at? I was bragging on my website. Let me see. I'm going to have to scroll down a while, because I don't see 55. Yeah, let me see. I have to scroll down far to get to 55. I don't know. Let's see. Degrees of freedom. 0.01. It's just telling us how to do it. Well, I don't even see the answer. All I see is, let me go back. Yeah. All I see here is once we do that, it gives us the code we would need. Look at this. Like I don't, because I don't see an answer here unless it's up here. Nope. It gives us the code we would need to do that in Microsoft Excel or Google Sheets to find the right and the left. I don't know why it's not just like showing up for us. But I can type this in to Office. I gotta find Excel though. It does start with an E, I guess. I apologize, this is taking so long. I should have picked an easy problem. Okay. So I'm gonna get it from there. I might just have to type it in. Okay, that was 1. And then Didn't that give us that gave us, wasn't the one we wrote down 63.5? Was that it? Was that the first one that the other website gave us? Yes? Close. It's probably the way that it calculates it and the rounding that it does, but we can still use that. All right. So we have this as the one for we have that. The one for this one here. What was the other one? Let's see. 46.03559. Let's just make it 06.036. All right. So now we're going to calculate it. Got everything we need. I'm wondering. Yeah. All right. So n minus 1. What's that? 55. Times s squared, 0.15 squared, over. All right. Which one do I put here? Is it 46? Yeah. Again, if you get confused on whether you're putting it in the right place, when we get the two answers, the bigger answer goes on the right and the smaller answer goes on the left. So it's not really going to matter unless you put it in wrong. Huh? 60, oh, was it 8 or 6? Yeah, did I write it down wrong? Oh, you mean putting this right here? Yeah, it's probably not going to matter. That is going to make it smaller, so yes, it actually would be. But again, once we find the two, as long as we put the bigger one on the right and the smaller one on the left, that's all that matters. All right, so let's do that. We took so long on the problem, I think it might have logged me out. Let's see. Yeah, I'm not really worried. But the homework actually logged me out because it took so long. All right. So I got 0.134. And what? Point, if I do 3 decimal places, 0. I must have messed up. Let me do it one more time. I think I didn't take square root. That common mistake. Yes, I didn't take square root. 164. All right. So it's not too bad.